Okay, so this is my video for standard 5.4. I forget which problem number this is, but they give us this wave function written in the position basis and ask us to find the probabilities of measuring the nth energy and the expectation value of energy. So before we do anything, we have to normalize the wave function. So that's what I do right here using our normalization condition for continuous phases. I just make a little u substitution to make simplify the interval a little bit, and then it's pretty a fairly standard integral. Once you square this out, you get a polynomial, and then you can use power rule. So doing that, you get that the modulus of our a needs to be the square root of 840 over the length of our box. And then we just choose the real number that has that modulus. So therefore, we know that our normalized wave function is this. Okay, so now we need to rewrite the wave function for the energy basis for the infinite well. So first we need to see how much of our wave function is in the direction of the nth energy value state, and then we know the wave function for that is right here, also in the basis. So what we're looking for is just this integral. So again, we make the same u substitution, u equals x to the l, and it turns into a pretty nasty integral. And then we just have to crunch through the integral, and we get all the each term has a cosine of m pi in it, so we know that this is. When we take the full series for the state vector, it's going to be an alternating series. So since our arbitrary, since the direction of our state vector and the direction of an arbitrary energy eigenvector exists, our state vector is the sum of that term over n. And we differentiate between odd and even terms, kept to the cosine of m pi, and then you can just rewrite that as an alternating series. So yeah, this is our wave function rewritten in the energy basis. So now to find the probabilities of measuring the n. So the probability of measuring the nth energy state will be just the nth component of the state vector squared, since we've already written it in the energy basis. So therefore, the probability of our nth energy eigenstate is this. Another pretty nasty expression. I thought about rewriting it to make it all this term in here all over n squared pi squared, but it didn't really make it look that much better. So I just left it like this. So then we know the energy value of the nth energy state. We can calculate the expectation value pretty easily by summing this probability over n multiplied by the energy of the nth state, which we know. And yeah, that's it for this video.